turn it off. There you go.
Yeah?
Very well.
Okay. Right, we restart. Electric and magnetic dipoles. So, yeah, we've got this analogy between the two systems, and if you end up with a dipole in an external electric field, of course there's a torque exerted on it that tends to pull it parallel with the field. And likewise, if there's a magnetic dipole in a magnetic field, there's a torque that tends to pull it parallel to the magnetic field, and you can express that in terms of the energy as well, rather than, you know, the old kind of force type description, and say, well, the dipole has got lower energy if it's lined up with the field, and this is precisely what the minus sign is here. And again, just to recall to you that this looks a bit odd, but the original definition, the dipole goes from the negative to the positive, so this actually is lower in energy when the dipole moment is parallel with the field. And we have a very similar expression for the energy in a B field. Now, where I already flagged this up on Wednesday, magnetic materials are a bit more complicated, is that dielectrics are always attracted into a non-uniform E field, but ordinary matter can be attracted or repelled by a non-uniform B field. And that's where I'm going to just start, and this is with figure 125. Now actually this experiment would be extremely difficult to do in practice. You've got to imagine that this small piece of material is suspended completely statically in a static magnetic field. And of course, if you actually if you switch the magnet on beforehand and then move this piece of material in, you get Faraday's law type effects. We're moving a piece of material into a magnetic field, so it's cutting field lines, so we know there's a dB by dt experienced by the material, and therefore a circulating electric field, and that sets up currents in the material. And the Faraday's law type effect is, if you like, beyond what we can cover. So you can't get around the problem the other way by, you say, well, I could make this an electromagnet and put this, you know, in the middle of the field and then switch the field on, because then I've got a dB by dt because I'm changing the field strength, and also I will induce currents. But let's say, for example, that this string, as written here, is rather rigid. We've got the field switched up to full strength, and then we somehow release a clamp, and we see what this piece of material does in the static magnetic field. Well, electric dipoles would always be attracted to the region of high field strength, but this can go either way with any type of material, depending on what's inside it. And this is where we get, of course, we're starting to run now into quantum mechanics and running out of what we can say with the classical field theory. Nevertheless, I'm going to pursue the classical theory for a short while, because it does produce one important result which is actually useful even in the quantum mechanical case. So first of all, to say, and this is a big difference, unlike dielectrics, which are always attracted into a non-uniform E field, and again, I've mentioned that it's important in this case that we're actually considering non-uniform fields. I mentioned this before, that if we have a completely uniform field, in other words, we set up a parallel plate capacitor, well, if we put a dielectric slab in that, it gets these surface polarization charges, but the pull between these charges, and so the dielectric slab's pulled equally and opposite in the two directions. So in a uniform E field, it's not attracted, but it moves in a non-uniform E field. Well, this is now very different, because ordinary matter has two types of magnetism. So this is, the raw facts. I should say that the coverage that I'm giving of magnetic materials is given in a different spirit to the electric materials. There's no more in the course in third and fourth year on electric properties of materials. The bit you know is plenty. But of course, magnetic materials are used in a huge variety of applications, mostly in storage of information. I mean, a company like Seagate has now sold over 2 billion hard drives. So we're talking about, a massive worldwide industry in terms of controlling the magnetism of materials. So all that I'm going to be able to do is give you the the kind of phenomenological overview, the way we describe magnetic materials. There's a third year course on electrons in solids that many of you will take. And if you're on the fourth year course, there's a fourth year course on magnetic materials. So the behaviour of electrons in solids, particularly due to spin-orbit coupling of electrons, which is way beyond the kind of classical field theory that we've done, and indeed slightly beyond the quantum mechanics that you've done. I don't think you've covered spin-orbit coupling with Christian this year. It means that we can't go too deep into the subject. So I'm just going to introduce, if you like, the terminology, and then you'll have to go on further into magnetism if you really want to understand it in depth. So diamagnetic materials, these two types of materials have got specific names. Diamagnetic materials, e.g. bismuth, so many choices that I could have made. Bismuth has got no unpaired electrons, so it has no, if you like, orbital or spin angular momentum in its ground state. And all substances like that, where the ground electronic state of the system doesn't have unpaired electrons, are repelled by a repelled, let's say from the high field region. If you like, this is basic fact number one. And most materials are indeed in this state. As we know, I mean, even though you've not done much on chemical bonding, on molecular quantum mechanics, you should be aware that from elementary knowledge that you bring into the course, that you tend to get electrons paired up in bonds in solids, and so many materials behave in this way. Paramagnetic materials, this is, we'll see, aluminium has an odd number of electrons and has, if you like, an unpaired electron in the ground state. So again, I could have chosen a million examples, but as usual, I've followed the Feynman lectures and he chose bismuth and aluminium, so that's exactly what I'm going to do. These materials are attracted to the pointed pole. So right from the outset, we've got two different types of magnetism to explain. And I should emphasise from the outset, this is a purely quantum mechanical phenomenon. Again, a lot of people use a lot of hand-waving classical analogies of, there's somehow electrons are sort of spinning around, and we'll see that we can, to a sort of way, interpret orbital angular momentum in that way. But the classical analogy takes us a certain distance, and that's what I'm going to do next, is the classical analogy of magnetism. And it's an incredibly simple model, and that's illustrated in figure 126. So this one, if you like, refers to the previous figure, 125. That's just the raw phenomenon, if you like. Now, in classical EM, which is what we've been doing through the course, there is a definite relationship between the angular momentum, which we're going to describe by a vector J, and the magnetic moment. I mentioned this when I first did the definition. The full name is magnetic dipole moment, but you'll usually just see it abbreviated to the magnetic moment, which we'll call mu. And mu, as I've said, this point's perpendicular to the plane of the circulating current. So the analogy, once you've got that, we have, so in classical mechanics, just to emphasize that this calculation is classical, we have J, the magnitude. Again, I'm not going, strictly speaking, I should write the magnitude, but I'm just going to abbreviate the magnitude to J. We know where the directions are. This is equal to mvr. Sure, that's an equation everybody could have, written down, if you like, in pre-university physics, that the angular momentum of an object going round is the mass times the velocity times the radius. And of course we've got, just to recall, this was our classical result for the magnetic moment. This was a classical charge rotating in a well-defined orbit. We know this is not a great description of atoms, but we're going to pursue this for a minute. Mu, oops, sorry, get it the right way. Mu is equal to IA, where, if we want to make this connection, we can write that the current is Q times the velocity over 2 pi r. And this, if I divide the velocity in meters per second by the distance travelled, remember this is a completely classical picture, 2 pi r, if you like, I get the period of the rotation of the charge in seconds to the -1, and if the charge which is going around is Q, the current is given by this very simple formula, because you could imagine that at any point on the circuit I can just say, well, how often does this charge go past me? And it goes past me at this rate of coulombs per second. So again, these are all very straightforward algebraic equations. So this is the classical analogy of the system, and of course we've got A is equal to pi r squared. So we've got expressions for Q and A, which are very straightforward, and just by simple algebra, putting those together, we get that mu is equal to Q VR over 2. So this is now equation 32(4). So Q mu, so it's very straightforward, just algebraic substitutions, is Q over 2m times J. And now I'm going to very specifically write J orbit. This would be the relationship between a classical charge just going round in a circle. So this is like a kind of Bohr model of the atom, very unsophisticated, but at least it does give us a relationship which shows that the magnetic moment is proportional to the angular momentum. And in fact, if we just consider orbital angular momentum, this is also true in quantum mechanics. That's why we bother, if you like, with this classical analogy. But again, there are lots of caveats today in what I'm going to say. And so where we have specified that we are dealing with orbital as opposed to spin, angular momentum. So if you've got a charge Q just rotating in a circuit and you apply these simple classical ideas to it, you do get a relationship which is true in quantum mechanics for orbital angular momentum. So if you like, we've got some kind of analogy. Now you know that you've done enough atomic physics to know that electrons can be in S states where the orbital momentum is 0. We've got P states where the orbital angular momentum is 1. We'll come to the units in just a minute. D states where the orbital angular momentum is 2, and so on. So this is, sorry, move that up, this one down. This, however, so no, let's say explicitly that equation, let me number this up, equation 32.5 is also true in quantum mechanics. So this is a very, very important to note that this equation here, but I've had to specify this is only true for orbital angular momentum, but note that, important point, for electron spin, for which there is really, no classical analogy at all, mu is equal to the charge over the mass times J. So, if you like, this is what we would get just for a charge that's going round in a circuit, and we've got Q over 2m here. But for spin angular momentum, if you think of the Q over m out front, we have half integral spins. So, but at least, and this is the last sort of note I'll make up really on this analogy, in either case, the direction of the magnetic moment, so this is it's almost as far as we can pursue the analogy, because we've already got a relationship that we cannot possibly derive here, equation 32.6, from classical mechanics. Classical mechanics always gives us that we'd have Q over 2m, and then, of course, the charge to mass ratio of the electron, many of you will have measured in first year laboratories. This is a well-known constant, sort of typically around, you might, if you did a good experiment, 1.8 times 10 to the minus 11 coulombs per kilogram. This is a very well-known quantity, the charge to mass ratio of the electron, but we have no classical basis for understanding why we have this factor of 2 missing when we look at electron spin. So, but at least in either case, the direction of the magnetic moment, again, this is, I've only dealt with the magnitudes here, but the direction is exactly opposite. This constant in front is actually negative. Could view that as due to the negative charge on the electron. That's the way Feynman explains it, but I think even there's a little bit of hand waving. Is exactly opposite to the direction of the angular momentum. So, if we consider the electron just to be circulating in an orbit like in a Bohr model, we do get this relationship here between the magnetic moment and the orbital angular momentum. So at least that's taken us some of the way. Now, in previous years, I pursued the classical analogy a little bit further, and I'm not going to do that because it is rather inadequate anyway. this is the next figure, which I'm just going to pretty much gloss over, is to illustrate that this idea that Tor is equal to the cross. We can understand if something's going round, we imagine our electron is just sort of whizzing around some circular orbit, and we've put some external magnetic field on that exerts a torque. We've already had that equation. But you will have done this with Roddy in the Lagrangian mechanics, that the result of this is that the angular momentum tends to precess about the field direction. And in particular, it has a well-defined frequency. This omega subscript p stands for a precession frequency. This is as this vector, if you like, sweeps out this circle around the field vector b. And as you know from your work with Roddy, this actually has got a name. It's called the Larmor precession frequency. And particularly if you do nuclear magnetic resonance experiments, or indeed electron spin resonance experiments, this is often used, particularly by chemists who do, use this for spectroscopy. Look at the study of spins inside materials. You'll see this used, but it's really a bit of an inadequate model because you're assuming that you've got a classical precession. So in effect, this thing is just behaving like a little gyroscope. And the mechanics of the gyroscope are quite difficult. And being as the analogy breaks down eventually anyway, I'm not going to pursue that, but I thought I would mention it. And if you like, the origin of diamagnetism in the classical way looks like it's as illustrated in figure 128. So here we've got a magnetic field, and we're imagining that we have a charge which is circulating in some orbit. Well, of course, this charge this motion is sweeping out a certain area, that shaded area in the figure, as a function of time in a magnetic field. So it experiences a Faraday's law effect. It experiences, if you like, an induced EMF. So this is just the classical analogy. And we know that the induced EMF opposes the motion. So the hand-waving argument of the origin of diamagnetism is that because so if you like, you get an induced EMF, we've got a B field, and we're sweeping out a certain area in a certain time. So this is basically the rate of change of magnetic flux, which, as we've seen, is the EMF, and that the EMF always opposes the motion. So what you get is that the orbital angular momentum is reduced by a certain amount, and because this negative sign in the EMF, and so the magnetic moment that's induced is opposite to the magnetic moment of the spinning electron itself. Now remember, this has got some kind of because it is spinning in the field, this charge going round, we've just done the maths of that, we know that we get a mu which is certainly proportional to the angular momentum. Constant of proportionality is a problem if we have spin as the source of the spin angular momentum. But whatever this, so if you like, it's producing an inherent mu in this sense, but the Faraday's law effect produces an extra effect that opposes it. So we reduce the angular momentum by putting the material in the field. So if you like, to go back, and as I say, there's a lot of hand waving, because if you pursue the classical analogies all the way to the end, diamagnetism disappears and paramagnetism disappears. So although this is a perfectly reasonable derivation from classical mechanics, when you start to pursue it and pretend that I can apply Faraday's law to a system of a rotating charge, of course that's right, but the atom is a lot more complicated than a charge going round in a circle. And in particular, the reason I'm not going to pursue that analogy, although I will make a note on the, if you like, because you'll see this done a lot when you go further into magnetism, so I will make an explicit note on this. So, figs 127 and 128 illustrate the, let's put it in brackets, supposed classical origin of diamagnetism. This is how we try and understand diamagnetism in a classical context, and that is the induced EMF. That's what precisely figure 129 is there to illustrate, if you like, opposes the, and again they'll put it in inverted commas, motion, because we know an electron just spinning round at a velocity v, whizzing round in a circular plane round a nucleus is a very poor description that was that Bohr developed about 100 years ago and was soon superseded in the 20s by the Schrödinger and Heisenberg formulations of quantum mechanics. But in this analogy, the induced EMF opposes the motion, and the magnetic moment is, if you like, anti-parallel to the field. So the motion actually results in the system being repelled from the magnetic field, because this extra induced current actually opposes the motion, and because it opposes the motion, the system has got a higher energy state when it's in the field than when it's not in the field. For paramagnetism, if your material has got a magnetic moment, remember this is an induced magnetic moment, so most material doesn't have a magnetic moment to start with. If you put it in a field, you induce a moment that opposes the field, so it's repelled. If you have an inherent magnetic moment, this is like the different, you now go to a state that's a bit like, similar, not the same, as putting water in a dielectric field, that moment now does tend to line up parallel with the field and reduce the energy. Remember, we've got that this mechanical energy in the field is minus mu dot B. So if mu and B are parallel to each other, we now get a lower energy. So again, it's supposed to be the classical analogy, so we'll do it. The origin of paramagnetism in classical theory is that any permanent, remember this was due to, if you like, the induced. We induce, by the very act of putting this material in a magnetic field, we induce currents, and the currents oppose the field, so we end up with a higher energy state, so the material moves out of the magnetic field. However, in paramagnetism, the classical theory is that any permanent dipole moment in the material, and this will clearly be the case if we have unpaired electrons. So the electron spin now tends to align parallel with the field, and we get a lower energy state, so the material is attracted in. So any permanent dipole moment in the material aligns parallel with the field, reducing the energy. Again, remember U is minus mu dot B. So it's attracted in because it goes to a lower energy state. Now, there's no real analogies. Now, they start to break down because we have to hit now quantum mechanics. So first of all, this is just again, you don't need this, but I feel that there are some things where, as I say, I'm more trying to lay the groundwork for what you might do in years 3 and 4 than give you a complete picture of magnetism. So if you look at that equation, sorry, it was 32.4 in the VLE notes. I've made it 32.5 here. So that's the one that's on the middle board there. It's equation 32.5 in this lecture. We have got, of course, in classical mechanics, no way of understanding why the angular momentum is quantized. It can take any value at all. So we know that in reality, this is the fact, it comes in an integral multiple of h bar. And so, again, just to say to you, because obviously for n is 1, if there's 1 unit of angular momentum, so that would, example, be a single electron in an L state with a single unit of angular momentum, we have this fundamental formula that mu is qh bar over 2m. And because this combination qh bar over 2m occurs so much when you study quantum mechanics, you just multiply the two fundamental constants, the charge to mass ratio of the electron by h bar, you get a quantity which gives you the, if you like, joules per Tesla. That will be the amount that the spin, if you like, that the energy is reduced for an electron in an external field in joules per Tesla, and it's called the Bohr magneton. I mean, again, you don't particularly, I'm not testing that, I'm just mentioning it, that you'll see this Bohr magneton used a lot, because in every magnetic problem you get the charge to mass ratio and Planck's constant, because the angular momentum is quantized. But this, of course, is a derived unit. You can get it from the more fundamental units of these quantities. And the whole of classical theory, if you like, was destroyed by the Stern-Gerlach experiment. And again, did you study that in the quantum this year? Yeah, Stern-Gerlach. Well, good, because I don't want to go into it in detail. But if you send, what Stern and Gerlach did was that they had an oven and they had silver atoms in the oven. And again, all of like copper, silver, gold, they've all got an outer, for copper it's 3d10, 4s1, the outer electrons. For silver, you've got 4d10, 5s1. And you clearly, outside the filled shells, you've got a single unpaired electron. So if you vaporize your metal in an oven, you produce atoms which have got quite definitely a single electron outside the inner shell. So it's got quite definitely a magnetic moment. But you see, what we've been looking at, this formula, this lowering of energy, of course this is now writing out minus mu dot B explicitly, which is the magnitude of u times the magnitude of B times the cosine of the angle between them. Well, obviously the force on the atoms will be, again, I've made the magnetic, and look, this is also, remember, this is a very much an inhomogeneous field again, that's a pointed magnet, and this is a flat magnet surface, and let's say we choose the z direction to be the one that goes up through the magnet. Well, clearly the force is just minus du by dz, and differentiating with respect to z, we've just got here the only thing that depends on z is the field, so we've got a dB by dz. This is why it's important that it's a inhomogeneous field, because there has to be a variation of B with respect to Z in order to get this deflection. But the classical theory now is definitely wrong, because you could get, you know, well, why should this have any particular orientation with respect to the magnetic field? you've got all angles are possible in classical mechanics. So depending on the arbitrary angle with which the spin angular momentum enters the field, you'd expect just a continuous smear of silver atoms on the plate. You know, this is a continuous variable, and you just get a smear of atoms across the plate. Because you can imagine as we fire them into the magnetic field, some dipole happens to be like this, some like that, some like this, some like that, some here, some there, and there's my external magnetic field running through. Well, they can have any orientation with respect to each other. They've just atoms have come out of an oven. They could have any orientation. So we would expect, depending on that orientation, I mean this one, if you like, if we had one that was, let's find a different colour that might show up, brown chalk. If we had one that was exactly parallel, that would give the maximum deflection in one direction, that would give the maximum in the other direction, but everything in between would be possible. But we know from the Stern-Gerlach experiment, we just get identical two spots. So in other words, the angular momentum is quantized along the field axis, and that's why classical analogies of magnetism in the end break down. So you cannot get away from that, and what is really happening is that the angular momentum is quantized. Now again, it goes deep into the interpretations of quantum mechanics. This might illustrate interest physics and philosophy students, but certainly it's not something we can even begin to understand in a classical model, that the magnetic moment knows, this is in inverted commas, it's only allowed to take certain components in the field direction. Now the Stern-Gerlach experiment, because there was a single electron outside the closed shells, you get a splitting between the spin up and spin down states. There's only one possibility. If your angular momentum is a half, it can either be plus or minus a half. If J was equal to 1, we get splitting into 3 states. J is 1, J is 0, J is minus 1, which is the kind of thing you'll have done in the quantum mechanics. If you've got a 3 halves state, where you can have the J is 3 halves, J is a half, J is minus a half, J is minus 3 halves. But emphatically, in any circumstances, the angular momentum, if you like, its projection onto the field axis is quantized. And so we cannot explain this in terms of the Maxwell equations alone. Again, one of the reasons that I mention this Larmor precession frequency is that the energy splitting between these levels is often written as h bar omega p, and now that omega p corresponds to the classical Larmor precession frequency of a dipole precessing about the magnetic field. But you have to be very careful when you use that analogy, because really, again, if I have my field direction like that and my angular momentum and therefore my mu like this, and it's not really precessing about the field, because it's a quantized system. So this is why we don't pursue the analogies much further than this point, because actually once you get to thinking about what an atom really does in a field, it doesn't behave like a rotating charge. There's one point, I'll just come on to a little bit of phenomenological maths in a minute, but it's a very nice point, if I can find the missing view graph, my usual problem, is that there is, again, this experiment is incredibly difficult to do in practice because, again, you get a lot of Faraday's law effects. But if you start off, and we'll come to the properties of iron, needs a whole lecture of its own, which we've got next week on ferromagnetism. But let's just say, for the time being, that we can imagine, and it's not far off what happens in a ferromagnet, that we've got every single, I mean, this is a slight simplification, as you'll see, but that we've got every single spin in the material lined up parallel. And this will give us, obviously, a large net magnetic moment. All the magnetic moments are parallel to each other, and a bar of iron does have a large magnetic moment. And because it has a large magnetic moment, it is true that this must correspond to some kind of angular momentum. Now people say, oh, you know, quantized angular momentum isn't really angular momentum. You know, it's a different sort of quantity. But again, if you were to then put this in a very large magnetic field and do the experiment very carefully to avoid the Faraday's law effects, and you put it in a massive external magnetic field in the opposite direction, you can flip all the spins over. Of course, we are getting a lowering of energy by the spins being parallel to the field. So the spins will turn over. Now, if you do that experiment very carefully and turn all the spins down without producing too much in the way of Faraday's law effects, the whole bar of iron, and this is an experimental observable fact, it does start to rotate. So it really is a kind of angular momentum. It's not an angular momentum that's due to a rotating charge, because we couldn't explain precisely, we're talking now about electron spin, and remember in equation 32.6 we've just no basis whatsoever, we just have to accept that, if you like, as a fact of nature. We can't explain equation 32.6 on classical mechanics. Classical mechanics will always give us 32.5, so we can't even get the constant right. However, it does correspond, the angular momentum is perfectly real. If you flip over all the spins in a bar of iron, the bar of iron rotates, because the angular momentum of the universe is retained, and so that if you change the angular momentum of the spin system in one sense, the iron spins round, the whole block of iron acquires mechanical energy and spins in the opposite direction. So we're coming into, you know, a difficult realm in the last lecture on ferromagnetism, but I'd like to finish this one up just by, we got in the last 5 minutes, is the phenomenology of explaining paramagnetism, because that is similar to ferromagnetism. Ferromagnetism, we've got the spins, if you like, lining up parallel and the field enhancing, and in both, if you like, ferromagnetism is very, very strong paramagnetism. So the development of the classical theory of paramagnetism will be useful to us next week, and I shall make a little note on that. So let me just I'll go back slightly. I've missed out some of the notes on the VLE, particularly on the, as I say, on the classical analogy part of this lecture, because in the end, you know, all these quantum effects are rather beyond what we could, you know, hope to explain. So the let's just cut to the so in paramagnetism, we describe the field produced by the dipole moments in terms of, it's called the magnetization vector M. And this is very similar to the definition of the polarization vector P in dielectric materials. So the ratio of M, a magnitude of this vector, to B for small fields, I should emphasize this approximation, and again why I've not pursued it too hard, is it actually doesn't work for a lot of materials. However, it does work for small fields the ratio is called the magnetic susceptibility. And this is very similar to the electric susceptibility that we called chi, and indeed it's usually called chi subscript b. So the equation that's used is that m is equal to chi b over mu naught b. And again, I'll give it its VLE. I've missed a couple of equations out on this classical development. So you can compare that equation with that we had, this was chi epsilon naught E. So you can compare that. That's what we got. And this gave the polarization per unit volume in an electric field. This gives the magnetization per unit volume in a magnetic field. And you'll see again, rather unfortunately, just like the epsilon naught got absorbed into the definition of polarization, the mu naught got absorbed into the definition of magnetization. So this and this don't have the same units. So again, it's an awkward and messy field. The B field is in Tesla, as we know, and I'll come to this tomorrow. This magnetization field is in amps per meter. Now, chi B is positive, let's write the word out in full, positive for paramagnets, and that's just, as I mentioned, this paramagnetic theory is at least similar to the theory of electric dipoles. And so, of course, if you've got, like again, there's my sketches many times, there's my external electric field, where of course a water molecule is going to tend to line up with its dipole in this way and reduce the field. Here, again, we've got all these nasty sign conventions. For the paramagnets, what this corresponds to is that each individual atom is producing some spin, and these are going to tend to align parallel with an external B field. And for small fields, the field produced by the magnetization is indeed a calculable quantity. But we also apply the same equation with more or less no justification whatsoever to diamagnets, and it leads to the almost absurd result, but you'll see this in many textbooks, that chi B is negative for diamagnets. So most material, and I'm sorry if this lecture has been slightly confusing, I've tried to cut through. But the fact is that you'll often again see this written, that because in diamagnets you get repulsion from the field, it actually corresponds to the susceptibility in this equation. The only way that you can make everything hang together is by making this an inherently negative number. So for example, bismuth will have a negative magnetic susceptibility, but aluminium will have a positive susceptibility. Iron, which we're coming to next time, has a susceptibility which is positive, but several thousand, and I emphasize many orders of magnitude, between 1,000 and 1,000,000 times greater than for any other paramagnetic substance. So we'll come to the origin of that. Exciting finale to the course next Wednesday, and then do a bit of revision.